going to show you how to take integrals of some functions that normally up to this point we would not have been able to take the integral of. For example, this is the integral of sine to the fifth of x dx. The whole idea here is, remember, that's the sine function raised to the fifth power. So the inside function is the sine function. Normally I've got to have a derivative of the inside function. A derivative of the inside function here would be cosine of x. That's got to be multiplied on the outside for me to be able to reverse the chain rule and take the integral. So normally you look at this and you say, well, you know, there's no way that I can possibly take the integral of this. However, we have these three different trig identities up here, often referred to as the Pythagorean identities. And if you notice, there's one relationship that has both a sine squared of x and a cosine squared of x. Basically, sine and cosine both are integrals and derivatives of each other, just with signs adjusted. And so as a result, if I can rewrite this as a combination of sines and cosines, I may be able to write this in a way that I have a derivative of an inside function. Okay? What I'm going to do here is notice that these involve even powers of the function. So basically for every sine squared I have, I can make a replacement that involves a cosine squared. Notice that I have an odd power here, and that's crucial. What that's going to allow me to do is it's going to allow me to keep one sine to basically serve as my derivative of my inside function for when I try to reverse the chain rule. And meanwhile, I'm going to replace the other four sine functions with something from up here. So basically I can rewrite this just a little bit differently. Basically that's going to be sine to the fourth of x times the sine of x dx. Sine to the fourth is the same thing as sine squared squared. Okay, so I'm going to rewrite that as sine squared squared. And what I can find out here is that sine squared of x is equal to 1 minus the cosine squared of x. And I can replace my sine squared with 1 minus the cosine squared of x. Now, here's where my problem comes into play. I'm going to have 1 minus the cosine squared of x. That's a FOIL problem, okay? So I'm going to have to use FOIL. It's 1 minus the cosine squared of x times 1 minus the cosine squared of x. 1 times 1 is 1. 1 times negative cosine squared x minus another cosine squared of x is minus 2 cosine squared of x. And then negative times negative is a positive cosine to the fourth of x. That is what is going to go in place right over here. So what I actually get is the integral of, and be really careful with your parentheses. You've got to have parentheses in this whole thing. This whole thing is being multiplied by the sine of x, and if you lose the parentheses, you're not going to be able to finish this problem. So it's going to be 1 minus 2 cosine squared of x plus cosine to the fourth of x. All of that multiplied by the sine of x dx. And what's going to happen here? The distributive property really comes in handy. This gets multiplied by the sine of x. This gets multiplied by the sine of x. That gets multiplied by the sine of x. What does that end up doing? It ends up giving me the integral of sine of x minus 2 cosine squared x sine of x. Okay? This is linked to the derivative of the inside function. I've got to have that. Plus cosine to the fourth of x times the sine of x. All of this technically dx. And now what I can do here is I can go through, I can split this up really into three integrals, okay? I'm not going to write it out that way, but you know, basically I can take the integral of each of these parts separately. So the integral of sine of x, of course, is just negative cosine of x. And then this is going to be, it's cosine squared, okay? The derivative of cosine of x is going to be the sine of x. So there's my derivative of my inside function. Again, you may want to rewrite it like this, but that is the derivative of my inside function. So when the chain rule gets reversed, that's going to get sucked back up in, basically. And so the power raised by 1, I'll divide by my new power. That's going to be minus 2/3 cosine cubed of x. Again, sine of x is gone because of the reversal of the chain rule. And then finally, plus, now again, I have a cosine of x raised to the 4th power. We've got to be careful here because the derivative of the inside function, wait a second, I think I missed a sign over here. If you go back over here, the derivative of the cosine function is negative sine. So I need a negative sign here, which means I need to balance it with another negative out here. 2 negatives make a positive. That's actually going to turn this into a plus. You really, really have to be careful with your signs when you do these problems. And again, I need a negative sine of x as the derivative of my inside function here. I need to balance that with a negative out here. So that's going to be minus, I'll be raising the power to 5, dividing by that new power. So that'll be minus 1/5 cosine to the 5th of x, and then plus c. And that's my final answer. So again, it's a little bit strange, but the main idea is there's this very close connection between sine and cosine as far as having a derivative of an inside function. And as a result, we can use this relationship to make a substitution and simplify it. In my final example, I'm going to take the integral of secant of x to the 4th dx. Same kind of thing as before. Normally I need a derivative of an inside function because this is really secant of x being raised to the 4th power. The derivative of the inside function would be secant x tangent x. And while I could borrow one secant x, that doesn't give me a tangent x. So again, what I can do here is I can try to make a substitution. The difference here is there's a link between the secant function and the tangent function. I can make that substitution. For every secant squared, I can replace it with the tangent squared x plus 1. One place that this is going to be a little bit different is the relationship. I'm going to be replacing it with the tangent. The derivative of tangent is secant squared of x. I need a secant squared on the outside of parentheses. In my last example, I needed a sine or a cosine outside of parentheses, not a sine or a cosine squared. But the derivative of tangent is secant squared. I need a secant squared on the outside. And that's why I can take this integral if I have an even power instead of the odd power like I had with the sine and cosine function. So I'm going to borrow one of the secants. I'm basically going to rewrite this as secant squared of x times the secant squared of x. And I'm going to replace one of those with this value right here, okay? Again, that sum needs to go in parentheses. So what I have here is a tangent squared of x plus 1 times a secant squared, that's a 2 there, dx. And when I use the distributive property here, again, really, really, really important when you do this. But basically, I'm going to end up with a tangent squared x times a secant squared x plus a secant squared x dx. And fantastic things happen here because this is tangent squared. The derivative of the inside function, the derivative of tangent, is secant squared. Okay? The chain rule is going to be reversed when I take the integral here. And so the power will be raised by 1. I divide by the new power. That's going to be a tangent cubed x divided by 3. So right, that is 1/3 tangent cubed of x. Okay? Derivative of the inside function gets sucked back into this function basically when the chain rule is reversed. And check this out. Again, you look at that and you think, oh, this is going to be terrible to take the integral of. No, it's not secant squared. Secant squared is just the derivative of tangent. So I just have plus another tangent of x plus c, and I'm done. So this one looked like it was going to be terrible, and it actually worked out really nicely. Now, you know, if it was a secant to the 6th or something like that, I would need to do a secant to the 4th. secant squared times secant squared, and I would need to put the square of this in, and I would have to use FOIL and do it a little bit more like my previous example. So be on the lookout for these situations. The replacement between the cotangent and the cosecant is very similar too, because the derivative of cotangent is negative cosecant squared. You need a cosecant squared derivative of an inside function on the outside of parentheses as well. So I'm not going to do an example of one of those, but it's almost exactly the same thing as what I had in this example. So hopefully that helps.